Of course, there are numerous other hazards that science is helping us prepare for. For instance, the threat of a devastating pandemic. Fortunately, scientists think they have a plan for that too. But, and it's a big but, it involves re-engineering one of nature's most feared organisms. A virus. So that it fights on our side against pathogens. My father was engaged in research. He used to take me into the insect house where he kept mosquitoes infected with tropical diseases. This worried me because there always seemed to be a few mosquitoes flying around loose. Back then, if you contracted a dangerous disease, you could die before medics found out for certain what it was. Today, diagnosis can still take too long. It can take days between a suspected outbreak and a positive lab report. And in that time, an infection can spread like wildfire. What we need is a way to instantly identify these pathogens so we can stop them before they get to us. In Birmingham, England, an ultra-fast detection system is undergoing trials. Jim Al-Khalili has bravely volunteered to put it to the test, to uncover if it really can improve our chances of survival.
Outbreak. A deadly infection claims its first victims. Cause unknown. A new strain of virus, a lethal bacterium, even bioterrorism. There's a race to find the source, identify the threat, or risk an epidemic. This isn't fantasy. It could happen at any time. The problem is finding the cause of an outbreak can take up to 2 or 3 days, and some of these bugs are deadly. Some microorganisms mutate at alarming speed. In the war on bugs, the enemy has the upper hand. By working with one of nature's predators, biotechnologist Professor Tim Dafforn and his team may have found a way to turn nature against itself.
So, Tim, the challenge, I guess, is to detect pathogens, so any microscopic organism like bacteria or viruses that cause infection, as quickly as possible.
Yes, and to do that, we take our inspiration from biology. So life's been on this planet for billions of years, and during that period, it solved most of the problems which are currently facing man. So we look back into biology and attempt to use biology to speed up this detection in a really big way.
The hope is that by adapting nature at the nanoscale, they can find a solution for a serious human problem.
We work on a virus, and our virus is M13. So M13 is a long, thin virus, and it's completely inert. It doesn't cause any disease in man, unlike the viruses we know about, like HIV and hepatitis. Now, we've engineered that virus. So we've added another part of biology. This is an antibody, and an antibody is part of the natural immune system in human beings that hunts down bacteria. So what we can do is we can add that to our virus, and we now have a virus that can hunt down bacteria. When it hits the bacteria and finds the bacteria, it wraps around the bacteria, and we know that there's a pathogen there.
So you're basically re-engineering an otherwise useless virus and turning it into something useful, a heat-seeking missile that seeks out these pathogens, wraps around them, and you can instantly see that that's happened.
Absolutely. I mean, we can do this test in seconds. It's as quick as it takes to actually make the reading, which is very quick indeed.
So far, Professor Dafforn and his colleague Matthew Hicks have designed a machine that can detect a variety of one of the most dangerous bacteria, E. coli.
So, here it is.
Well, that's it?
Yep.
But it looks so simple. So how does it work?
Well, we've simplified the test, and one of the key things for us is that it's easy to use.
Right.
So, why don't you take the sample?
The scanner uses light to see whether molecules are lined up or wrapped round each other.
And what's going to happen is the sample, as you inject it, will go through this flow cell. The molecules will line up, and the laser that shines through, so there's a laser, if we just have a look here. So the laser will pass through the sample differently if the molecules are lined up or if they're not lined up.
And that'll show on this display?
Yeah, so in this case, because there's no pathogen there, we're seeing a signal.
There's a very clear spike.
The graph is counterintuitive. If no E. coli are present, the viruses align in the flow of liquid, and some of the light from the laser is absorbed, which the graph shows as a spike. If E. coli are present, the viruses attach to the bacteria, forming clumps and prevent alignment. Light travels straight through, and the graph shows a flat line.
We've gone from a lab full of sophisticated instrumentation and equipment run by dedicated scientists to something tiny on your tabletop. I mean, that is really impressive.
We've seen that it works in principle. Now let's put it to the test.
I'm on my way to the hotel I'm staying in, with dozens of people coming and going and food being prepared. A hotel is the ideal breeding ground for germs. So I've brought with me some of these. They're swabs for taking samples. Let's see if we can find some E. coli.
There are many kinds of E. coli bacteria. Some are harmless. Others, transmitted through contaminated food or water, can cause serious illness. We've commandeered the lobby to run the tests. Our first sample is from the hotel elevator.
I genuinely don't know if we're going to find any E. coli. So, Matt, can you run this sample then through your tester?
Yeah, let's have a look.
We're searching for one of the most dangerous strains of E. coli, called 0157.
Jim, why don't you run that through the scanner?
Ingesting contaminated food or water can cause bladder infections, kidney failure, even death. Tiny amounts of 0157 could trigger a major outbreak.
And the good news is that we don't have it here.
The spike is visually showing us the all clear.
So sample number 1 is negative.
Yes.
Okay, well, let's move on to the next sample then.
It's from the door handle to my hotel room.
And we're all clear again.
In England alone, there are 30,000 cases of E. coli infection every year. The deadliest ever outbreak was in 2011 in Germany. 53 people died. But thankfully, the sample from this toilet is negative.
We've taken samples from across the hotel, and in a matter of minutes, rather than days, it's given us the all clear. We haven't found that particular deadly bacteria. Where's this going next?
Well, the really exciting thing is the fact that we can develop this test for lots of different types of bacteria and viruses and other molecules, all at the same time within the same test.
So not just looking for this particular strain of bacteria, but things like SARS and MRSA?
Exactly. And we've already seen that you can move this device around, but even more than that, we've got a prototype of a new device that's going to be even more portable.
Well, that's really impressive, having a device that can carry around in your pocket. It's an exciting thought. By re-engineering nature down at the molecular scale, what we can do for E. coli today, we'll be able to do for countless other diseases in the near future.
A decade from now, it could be in hospitals, surgeries, and out in the field.
I am certain synthetic biology will be at the heart of our future. And not only will it transform medicine, I've heard how genetically modified microorganisms can be implanted into fabrics where they feed on human sweat, making clothes self-cleaning.